And I have kind of 50 minutes, yes?
Sorry, yes, yes,
Sure. Okay, and do you see my mouse on the screen?
yes.
Okay, so I can show something. So, okay, thank you very much. Thanks for the invitation. And let me try to drive you a little bit in between of p-Adic theory and, let's say, physics of the real world, which we observe. And my attempt will be to show that there is a connection, which we don't understand pretty much, but we are trying, we are pushing forward to this. We see some coincidence, maybe, we see some stuff which appears to be nicely matching from p-Adic story, especially from p-Adic strings. We see something from, especially from non-local gravity series. So I will try to explain the following story in details, how we can treat non-local field theory amplitudes. Why are they important, first of all, and this will take the major part of my talk. And then I will explain why I'm concerned about p-Adic string theory in regard to non-local field theories. And this is mainly, all of this is mainly based on papers in collaboration with Ravan Kumar, Alexey Starobinsky, and Anna Tokareva. With these people, recently we have put a set of results on the subject. And so here is my short introduction, just to emphasize the main points. The grand problem which drives me in this direction is that generically in our physics community, we want to quantize gravity, because still there is no quantum theory of gravity, and still gravity is only classical theory, and still there is no good approach to make it quantum. Even though we kind of expect that it should be quantum, or at least I belong to the community which expects that at high energies, gravity is quantum theory. So we are on the way of building quantum gravity. We try to do this. And on this way, we observe that p-Adic string action, in particular, is an object which arises on the way of constructing quantum gravity. And at this moment, I'm asking a question, what can be quantum p-Adic string? And I will explain later that in principle, p-Adic string is not a very well-defined object. It's a very good toy model. I would say it's a pure toy model, as I will explain why it is pure toy model, but nothing more, even though it has very remarkable properties. But before I will come to p-Adic strings, let me try to explain why at all I may need something like non-local or infinite derivative action to quantize gravity, because this is my logic connection. I want to quantize gravity. On the way, I meet something like Lagrangian with infinitely many derivatives. I observe connection with p-Adic strings, and I want to employ something what I know from p-Adic strings to say something about possible quantization of gravity. What is the problem about quantum gravity? Problem is very simple. Whatever we know about gravity is still classical. It cannot be quantized. And whatever have people tried doesn't work yet. Einstein developed very much nice gravity theory. It reflects a lot of observations of the real world, and it cannot be made UV complete, or in other sense, it doesn't work at high energies. So gravity is pure, Einstein's gravity is purely classical object. We cannot explain anything at high energies with Einstein gravity, and as such, we cannot make it quantum. We don't understand, for example, what is the interior of a black hole. We cannot explain what could be before inflation. we cannot, as such, answer many questions about gravity, even though some of them, like black holes, we most likely can really observe. And definitely we can observe primordial inflation, which means that most likely before inflation it was very high energy density state, and we don't know what it was exactly. On the other hand, those common with gravity theory know that people are trying hard to go beyond Einstein's gravity, and one of the easiest way to go beyond Einstein's gravity is to add other terms to gravitational action. And it was a remarkable advance by Koshelev in 1977 and 78. There were two papers in which he showed that R squared extension of gravity theory is renormalizable gravity. So for people who do quantum field theory, it means a very good success. It's a great advance. But it was apparently found that it is impossible to eliminate a ghost, a particle which features negative kinetic energy, and the particle which as such destroys your theory, because with any of its propagation, it somehow takes energy from the vacuum state, and as such vacuum is destroyed. Not great at all. In physics, we name it. In physics, we name such particles ghosts, and if they are present in the theory, this most likely means that the theory is sick. And normally you don't proceed with this. But here it was kind of, not like people wanted to proceed with the theory, but they kind of hit the wall that it was the only, you see, 1977, it's 70 years after theory of Einstein. And you see, in 70 years, it was only one proposal how to make at least some advance on the way to make gravity renormalizable, or let's say better from the quantum point of view. And definitely people paid a lot of attention to this development, even though it was obviously sick because of the presence of the ghost. I name it here Weil ghost because it originates from presence of Weil tensor in the action. On the other hand, from purely classical consideration, Alexey Koshelev has developed model of inflation roughly the same time in 1981, 1992. His papers appeared, and this model of inflation explains practically what we see in the sky, and it does it pretty well in a sense that up to now, so 40 years from the development of this work, which was totally theoretical development, it is just the best fit of all observational data, and this is definitely great. But we must say that this is purely classical development. And this development did not aim at making something, didn't aim at saying something about quantum gravity. But surely it would be great if we can say something, especially not so bad as ghosts, about quantum picture here, because maybe we can use something from this, or maybe not. We don't know yet, but let us see what we can do. And people, as this is some set of names, people try to do a lot of things. And one of the development, which was kind of very interesting, is an attempt to introduce infinite number of derivatives in a physical theory. Before recent times, it's considered like a bad idea, and definitely it's a bad idea from all canonical textbooks point of view. But I will try to explain you that maybe it is not very bad. And we'll show you that it may be a chance for us to construct something beyond previous century developments. And this is my motivation why, especially for gravity theory, I would be happy to have infinite number of derivatives. And then I will remind you that p-adic string model is exactly a model which contains infinite number of derivatives in its kinetic terms. So in principle, we already have an idea that infinite number of derivatives can arise in a model. The only point that when we, when you speak about string theory or some effective model of strings like p-adic string theory, it's something beyond our observations or experiments or whatever. It's as many scientists name it, it's a very nice mathematical game. Even like Green, Schwartz, Wheaton accepted in their book, string theory is a very good mathematical theory, but we are very far from physical reality of the world. Gravity, on the other hand, is our reality. We live in the world which gravitates. And in majority of our world, we live because there is gravity. And for example, we attracted to the sun, not so bad property for gravity. Maybe, and also we know that Einstein's gravity, in particular, the step after Newton's gravity, works pretty much well. One of the notorious example of Einstein's gravity to work is working GPS device. It works because of post-Newtonian corrections, and otherwise it would not. So we know that we are moving forward here. And here I try to present you some picture, which is very much general. I just want to say, look, let's imagine that I don't know anything about gravity and I will write this particular action, which would include any object which I can compute, which I can construct based on curvature, and which I can construct based on covariant derivatives. And these are objects provided by my geometry. And I will combine them in a nearly intractable and nearly everything including form. You see, it's some infinite product and then infinite summation over everything you can imagine. We don't know pretty much about this object, but surprisingly, we can deduce from this what will happen if we are interested in perturbations around maximally symmetric spacetimes. In geometry, maximally symmetric spacetimes, in practical words, are Minkowski and de Sitter spacetimes. And this we can do. So as long as we consider maximally symmetric spacetimes, we can conclude, and this was done in collaboration with Tirto, Biswas, and Anupam Mazumdar in these two papers, that this action, these two lines action, is something responsible for linear perturbations. Linear perturbations is a very much important object in all this business, because exactly linear perturbations tell you what is the spectrum of your theory, or in other words, what are the particles in the theory, and how do they propagate. So this is let's say, the must which we must study. And maximally symmetric spacetimes, and especially Minkowski spacetime, is a spacetime in which we live. As such, it is very much important to study what happens. And the first claim which I do is that whatever you started with in these parentheses here, you end up with this action around maximally symmetric spacetime. And this is what you have to study to learn everything you need about propagator of particles and the set of particles for the spectrum. You see, what we obtained, of course, it contains Einstein's gravity, so we're good to go. And also it contains these objects, which combined of scalar curvature, second rank tensor, which is Elmas-Ricci tensor on our manifold, and Weil tensor. The choice of tensors is just matter of convenience, because Weil tensor is a nice tensor. It is 0 on a conformally flat background. And using L mu instead of Ricci tensor is well motivated, because this tensor is 0 on maximally symmetric spacetime. And these functions of the Lambertian operator, boxes the Lambertian, and these are just functions which are analytic at 0, so they're Taylor expandable at 0. So you see, the claim is that I need to study this, and this is all I need to know. The next claim is that I can make use of the symmetry properties of my spacetime, practically the Poincare symmetry, and I can find out what happens for spin 2 particles and spin 0 particles. And spin 2 is my graviton. And this is my propagator for the graviton, which is everything in between h mu, h mu. H mu is a field representing graviton. And whatever in between is a kinetic operator. All these letters are constants and all these squares are the Lambertian operators. You see, we are constructing, we are finding out that function of the Lambertian operator arises. And you see that if you just have a local theory in which fw is equal 1, this function is equal 1, then this p of box is nothing but just something like 1 plus box operator. So it will be similar to this box minus r over 6, the next multiplier here. And I will explain why it is bad. And this is exactly what Koshelev has observed. And I will explain why it is bad to have just some polynomial of box here, and why it is well better to have something more complicated with infinite number of boxes and as such infinite number of derivatives. So the same derivation can be done for scalar particle. I will not stop here for too long. Scalar particle is scalar excitation in modified gravity. In particular, it can be attributed to the field which drives inflation during early universe time. And it works pretty much the same way. And here you see, since we are talking about infinite number of derivatives, first of all, let me remind you that some kind of 170 years ago, thanks to Russian mathematician Ostrogradsky, it was understood that higher than 2 derivatives in Lagrangian is not a great story. It will generate ghosts, most likely. And in a, let's say in a plane writing, it will generate ghosts. And we will try on the way forward, we'll try to use the fact that in particular, Ostrogradsky's statement doesn't tell anything about infinite number of derivatives. And just to make the story complete, I will mention that in principle, there are models in gravity like Handesky model or other models which do have more than 2 derivatives, but they still avoid ghosts. It's possible in principle, but this requires heavy fine-tuning of the model. And on the other hand, string field theory, the model which explains and describes strings at interaction level, it is a canonical example of theory with infinite many derivatives. So in principle, we can try to go forward because we know something is working. We just don't know how much we can do it here. But here I will explain what the idea. The idea is that in principle, as long as we have more than 2 derivatives, generically theory becomes bad. And this slide explains you why it is bad. This is the example. The first Lagrangian is a good theory. It's very much a well-defined propagator of one scalar mode defined by box minus m squared propagator, which defines one massive particle of m squared mass, and this is very good. It would become bad would we have minus box or plus m squared, because minus box would exactly represent a ghost, so particle of wrong energy, and plus m squared would represent tachyon if m is real. But if we go beyond of this, totally beyond of this, and write something like 2 multipliers, like box minus m squared and box minus mu squared, things become extremely bad, because you can decouple these effectively as 2 independent fields. And these 2 independent fields will inevitably have opposite kinetic terms. One will have plus box, like here, and another will have minus box. There is no way around. And you can just show this algebraically in a matter of 2 lines. And this is what was done roughly 2 centuries ago by Ostrogradsky. You can do anything with this. One sign, this will be just 2 alternate signs, And so effectively, this theory is just one normal field and one ghost. And would you add here more factors? Half of them will be okay, half of them will be ghosts. And whatever is ghost is bad. And if you go now a little bit backward, you see that this is what exactly we observe here for graviton. For graviton, we have here box minus R of 6. It's already one factor of box. And would P of box just be constant plus a box? It is just next factor. And this is what exactly Koshelev observed 40 years ago in his papers when he concluded that R squared gravity, which required to add Weil squared term, is bad because it had a ghost, even though it was renormalizable, and as such, at least one physical property was satisfied from quantum field theory point of view. So you see, the question is, can we join all of this? And the answer is yes, we can. So this is a proposal. We name it analytic infinite derivative theory. And the trick is to include here infinite number of derivatives exactly in the form of exponent of entire function. Would it be exponent of entire function? It will have no zeros on the complex plane. Propagator is inverse of this, and being inverted, this exponent will not generate any pole. In physics, we count number of particles by number of poles of the propagator. And if there is no new pole, there is no new particle. So this way, we achieve two things. First thing is that we introduce more than two derivatives. Second thing, we don't generate any new particle at all. Things to mention here about entire functions, which all of you, I believe, pretty much know, can be formulated in short like this, that at infinity, which means when box operator, so momentum effectively of the particle tends to infinity, the propagator will feature essential singularity, because exponent of entire function will have obligatory essential singularity at infinity. And I will explain later why it is a tricky point, even though not a no-go observation. It is tricky. It is not like in canonical theory, but it requires special understanding. And now you see, let us return to the propagator of graviton, and let us write it in a most simple scenario when all this background curvature is zero. So when in Minkowski space, this is what we get. You see, as I just explained, this P of box, the only thing which it can be, it should be exponent of entire function. And if I say that P of box is exponent of entire function, it just means that since I started with Fw in my action, Fw must have infinite powers of box. So as such, I arrive to the point that in my action, which was a few slides before, which is exactly here, in my action, at least to eliminate tensor ghost, at least to make tensor sector, spin 2 sector well-defined, I need this function to contain infinite number of derivatives, and practically I don't see any algebraic way around. I should make some adjustments like normalize the function omega at 0 to be 0, but this is just a matter of achieving correct IR infrared limits. So in principle, it's not a restriction at all. So you see, what we now observe at this stage is the following. We can improve proposal by Koshelev by saying that infinite number of derivatives must enter here in the graviton propagator, which essentially means that we must start with infinite derivative gravity action. There is no obvious way around of this. And as such, the question is whether we can work and understand infinite derivative theory at quantum level. And as I said before, essential singularity of exponent of entire function is a tricky point. So practically question is formulated here. Can this be quantum gravity? We don't know yet, but definitely we know that answering this, we must answer the question, what is quantum theory of a model with infinite number of derivatives? And here I come to the subject which perhaps a bit more, maybe way more known to most of you, is the p-Adic string theory, which I declare to be the pure toy model. This is a model which was constructed roughly 30 years ago, Lagrangian, which was constructed roughly 30 years ago. And in several groups, this result was obtained, including Branko Dragovic, whom we're happy to have around during this meeting. And this particular model, as you see, it also contains infinite number of derivatives here by means of exponent of the Lambertian operator in the kinetic operator, in the kinetic term for the field phi. But definitely, one must accept that this is just a toy model to describe some properties of strings. Because what we observe here is a model which generates literally no degrees of freedom in the perturbative vacuum. It does produce degrees of freedom in the non-perturbative vacuum, or maybe on the way of rolling between these two, but on top of the real scalar field, it produces infinitely many ghosts. And this is very well known because a kinetic operator will have infinitely many zeros. Still, this doesn't forbid us to study this model, and what people have found that if we declare these aforementioned ghosts as spurious degrees of freedom, then what we restore for true tachyon, we restore the three-level scattering amplitudes of string theory, so-called Veneziano amplitude. And here there are two important words. First of all, we're only talking about tachyons, but it's okay, it's fine. We should serve at least something. But the most important thing, we are talking about three-level amplitudes. So technically speaking, we just observe classical scattering, which we can find out from path integral representation using just quasi-classical approximation. We are not going quantum, really. We will say that we are going quantum correct. We are going to consider quantum corrections as long as we will consider loops in this theory, which is not a trivial task at all. And definitely, I'm not going to consider loops here because this is a toy model explaining three-level scattering. This model will not make me anything good about loops. But definitely, I want to make use of this section like an inspiration for analytic infinite derivative gravity, which I explained before, because definitely this is a very nice starting point. And what I want to stress that it's not just a starting point actually, but this is something which makes a lot of connection to the gravity model presented before, because in the so-called weak field limit of gravity, what I will observe for my scalar degree of freedom is exactly action like this. Well, definitely it is not p-Adic action in its pure form, but definitely it has some similarities. And the most important for me is presence of this operator, some function of the Lambertian. But in my case, it is explicitly accompanied with a factor box minus m squared. And even if this will be some exponent of entire function, which I would like to have, This will generate me a degree of freedom, physically propagating degree of freedom. And so at this stage, I want to ask the following question. What is quantum theory with such a kinetic operator? Practically, I know the answer. The answer is that I just have to take from the shelf book by Ramon, for example, where phi to the fourth theory was explained very much well in a local case, and just repeat all the computations. And now I will explain you how tough it is. So the idea is to compute at least one loop correction in this action, task which was practically never been done before a few years ago. And even a few years ago, it was done only schematically by Ashok Sen and his collaborators. And we tried to move forward a little bit just to see what the kind of difficulty we should meet here. And now we're coming to really hardcore quantum field theory in all its beauty, because these are loops, and this is tadpole loop correction to the propagator. And this is the amplitude which we must compute, preferably for for unspecified function f, apart from the fact that it should be exponent of entire function. And here we already observe the surprise, which we named like fate of the Wick rotation, because Wick rotation is the only way of computing amplitude in field theory, in quantum field theory, even in local. Wick rotation essentially means that instead of using Minkowski signature, we go to Euclidean signature, and we are pretty good in this, because usually if we do it, we technically rotate contour of integration, replacing real line by imaginary, real axis by imaginary axis. And this is very well motivated because these large arcs usually produce us zero input to our integral. And this is very well motivated by Cauchy's theorem and by decrease of the propagator at infinity, but unfortunately only in a local theory. In our case, it doesn't work at all. Why? This is exactly because point of infinity on which this arc lies is exactly an essential singularity of our propagator, because exponent of entire functions is function of chi squared. It introduces exactly essential singularity here. So practically this contribution is undetermined. And in principle, it can be made any. And in principle, it is. We must say that in case of this simple Feynman graph, where we just computing this integral, we can arrive to this bottom line condition, which will make finally this big arc contribution 0 will advocate Wick rotation and will look like okay. It is not impossible to satisfy this relation such that this particular integral is 0. It is fairly doable, but the tricky point is that if we do it, we will achieve this only for this particular Feynman graph. And as you know, in quantum field theory, we can draw infinitely many graphs. So if we want to satisfy similar condition to any graph, we will arrive to infinitely many conditions. And this is definitely not what we want to do. And this is yet another Feynman graph, which we must compute. It's a so-called fish diagram, because it's in some way resembles fish in its drawing, even though it's not obvious maybe, but it's named always fish graph. And here we try to understand what to do. And procedure was outlined by Pius and Sen in their paper of 2016. The procedure is the following. The procedure is try to make all the computations in Euclidean signature and then analytically continue the results to Minkowski values. this most likely should work. At least this does coincide with what you get in a local theory. And this is what we try to do. And we try to compute the results at least for f of box equal exponent of alpha box, which is nearly p-adic string theory, apart from extra box factor in front of f of box in the propagator. And we did obtain some nice formula, which doesn't look like pretty, but it's fine, because this particular formula, which you see here, has very important property, even though it's cumbersome and it contains integral exponent. It has a property that is the limit alpha goes to 0, which means effectively f of box goes to 1. We restore the local limit, and in this local limit, we restore logarithm of z contribution, and this is what we know from local theory. So first of all, we restore local theory. Second exercise, which we did, we tried to do the same computation in just exponent of box propagator without even box prefactor. And we could easily show that we can restore Venetian amplitude. So we are very good to go with this approach. Things work. And the most important, we have restored optical theorem. Optical theorem is a little bit complicated notion maybe, but in short, it means that if I cut the graph in two, just physically by scissors cut this graph into two pieces, then imaginary part of my computation should be equal to the product of corresponding left and right pieces of the picture. And this holds. As such, we declare that method works and satisfies our expectation from a local field theory. And as such, it looks like we have made at this stage an advance, because we not only are able to reproduce Venetian amplitude, which is, let's say, at this stage, nearly trivial result, but we also could make sense to loop corrections, which is essential move towards understanding what is a quantum theory. We did even more. Here you see we computed for f of box equal just exponent of box. We tried to compute it for generic f of box, and especially it works well for even function f when f of k squared equal f of minus k squared. Let's say it's there is a reason why even functions work better than odd functions, and we have nothing against even functions, or at least we are happy that we could advance at least in something. Some integrals on the way look like terrible, but apparently they're not so. And this particular integral over dx over 3 Bessel functions can be performed analytically in terms of just fractions, which is a bit of surprise, but it does work. And in principle, we can write down nice answers. They're not even though more illuminating, but the point is that at least at this stage, we can employ some numeric methods for generic f of k squared and f of q squared. These numeric methods don't work pretty much well, to be honest, because everything we work with usually converges very slowly, and we must work hard to make them giving us some numbers. Or at least, let's say, like these canonical programs like Maple or Mathematica are not good here, but at least we have something. What is even more surprising here is that in principle, all this non-local business and all this contribution from f of box, let's say, and non-local effects doesn't matter in rough words, because it gives really corrections. And the dominant contribution is given by this last piece, which is extremely easy to tackle for any f of z. We can just perform this integration easily out there. Whatever f of z is, it's just one-dimensional integral. And we can obtain this result and as such compute amplitude of scattering through the loop correction. And we tried to do this, and we obtained sensible results, which are not so easy to check by some alternative methods. But given that all the properties which we expected are satisfied, so far we don't see any mistakes. And of course, we did try to do computations for easy form factor. And then we tried like exponent of p squared, so exponent of box. Then we tried exponent of minus p to the fourth, which means box squared, which worked pretty well and fast even for numeric methods. Then we tried this particular function. And just to mention here, gamma 0 is incomplete gamma function. And maybe a little bit surprising, but this combination like gamma 0 minus log is an entire function. And this function is of some special interest to us, but even for this complicated example, we could deduce some results which tell us roughly the following: that method works. This last integral gives principal contribution. The first integral gives first correction, and it does not, let's say, it is not important in the infrared limit and only becomes sensible when we reach the scale at which non-locality is essential. And the most important, the only imaginary contribution is here, which exactly satisfies the statement of the previously mentioned optical theorem, which requires a specific value for this imaginary part, dictated by initial action. And now let me go even further and let me see what happens if I do move forward. And if I not just consider some non-local action here, but rather consider also some potential, and even couple it minimally to gravity. And this is exactly what I observe in the weak field limit. And alternatively, we observe this in a non-local Higgs inflation model. So these two kind of coincide in this way. So in our non-local gravity, in a weak field approximation, which is responsible for, let's say, first beyond Newtonian, first beyond Einstein corrections, we observed that this is what we have to study for kinetic term. We gain some potential, and we have minimal coupling to gravity in terms of just Einstein gravity, and all the coupling between scalar and gravity goes through the square root of minus g. You see, what we obtain here is a very interesting observation that in principle, this theory can be well motivated. But we observe here, and this can be attributed to any theory, including for example, p-Adic string theory. We cannot just easily work with this object because you see, kinetic term, it contains infinitely many derivatives. And in principle, if we write propagator, we will observe as many particles, as many roots this equation has. And this equation depends on the second derivative of the potential. It is not guaranteed that second derivative of the potential is 0. And only if it is 0, this left-hand side generates only one 0 as its algebraic solution, and as such, only one particle. If the second derivative is not 0, like for canonical phi squared, for example, potential, then in principle, this equation would generate infinitely many zeros as roots, algebraic roots with respect to box. This is exactly what is observed in p-Adic string, and this exactly will correspond to a lot of ghosts. But what we have found here is that in principle, picture is not hopeless. And in principle, yeah, we can have ghosts. But for the time being, I would mention that presently people are more tolerant, let's say, to ghosts. They don't bother too much about ghosts. What they bother more is whether these extra particles are harmful or harmless, in a sense, whether they produce runaway or confined classical trajectories. And this is the condition that as long as we live in some de Sitter space, we must have the masses of these extra particles satisfying this relation that imaginary part of square root of mass squared should be less than real part of mass squared multiplied by the Hubble rate of our space, which essentially means as long as Hubble rate goes to 0, so as long as our space goes closer and closer to Minkowski, it means that all these extra particles must better be somewhere on the real axis. And this way they will, even though half of them will be ghosts, they will not disturb us too much. This observation, I think, is a very nice point here because it says that in principle, we can somehow advocate presence of such kinetic operator, even if naively it does, due to this equation, generate extra degrees of freedom. Because if these degrees of freedom have special properties, exactly like written here, and this condition looks pretty simple. I don't say it's pretty simple to satisfy it. No, it's not at all. It requires, looking at this slide, very special form of sigma. But if we do it, and it doesn't contradict any complex analysis statement, if we do it and if we invent such entire function, which is possible, and we can have some explicit examples, then in principle, we are good to go and we can advocate presence of such infinite derivatives, even being coupled to gravity. And as was shown before, this story can be developed up to quantum corrections, and these quantum corrections can be given treatment by means of special new prescriptions. So what I want to conclude here, that it's a class of analytic infinite derivative theories. And the main goal of considering this, at least for me, is construction of UV complete and unitary gravity theory. Generically, if we talk about infinite derivative gravity, it's a theory with great potential because it had a lot of nice properties from point of view of physics, roughly mentioned here, at least some of them. But what is more important for me at this stage, that we observe clear connections to string field theory, and in particular to p-Adic string theory model, which even though a toy model, it is extremely useful, or better to say the only so far well-developed model with infinite number of derivatives. And as such, I would say that we tried, and I believe we did, in fact, advance with respect to initial p-Adic string theory formulation, because we have shown how we can make it explicit computation of quantum corrections, and have shown that these computations are well motivated, can be done explicitly, and the results can be reused to think more about further quantum corrections, or maybe about other properties of the theory. And as such, for me, just yet more work in progress to be done. And here I will stop. Thank you very much for your attention.